Okay, Roberto, alias Robert Lee, has asked about this, and I thought I'd make a video to explain it. This is all to do with the AC generator. AC generator, which I taught a little bit to one group, and the other two groups never even started, I don't think. It's all basically how we generate AC waveforms. And you need to know the design of the AC generator and draw graphs showing linkage versus time for a spinning coil and get all this equation here. And that's the equation causes the problem. Anyway, the AC generator, you've got stuff ready on Edmodo about it, but you've got the coil here, which spins around and around and around. You've got your two slip rings here, and you get your AC waveform out. Now, the bit that I've been asked about is this bit here, and all these little gaps in my framework. Now, what you've got is basically trying to get hold of my simulation, rapidly trying to go through, is you've got a coil, and this coil, it spins round. I hope it wasn't a spin round. Did it spin round? And it's starting to, yeah, it's in a spin round. No. Oh, there we go. Start it. Yeah, it's spinning round. Fantastic. And that coil spinning round between two magnets, north-south pole. Now, as it goes round, you get flux going through, where if I pause it, the flux is going to be a maximum. Oh dear. No, that's speed. No, let's go back to manual mode, try and show it. The flux, can I do manual? Drag it. Oh, there we go. Do it this way. Right, the flux is going to be maximum here. Then the flux into the coil is going to be a minimum, and then maximum there. And I can show it through this, and this shows a flux through the coil, which is going to be 0 just there. It goes maximum here, and then 0 again. Now, like I was trying to show you before we broke up, is it's like going here, it's going to be BAN, there's going to be 0, and there's going to be minus BAN, 0 BAN. So what goes round is the flux changes with time. Then, if I go back to automatic rotation again, starting that, then you get this curve come out here. Now, the curve goes like this because it's going to change sinusoidally with time. We can be cosine or sine, depending where you're starting from. Very similar to what it did with SHM. Okay, but the induced EMF comes up here is going to be the rate of change of flux, which comes down to Faraday's equation. Now, very similar to what we did in simple harmonic motion. Here the gradient is 0, therefore the EMF is 0. Here the gradient is maximum negative, but now it's coming maximum positive here. And that's the equation, or the Faraday's equation, which I can't remember which groups did it with, which is basically minus n, the delta phi over delta t. So therefore, the gradient is a maximum, the EMF means negative of the gradient. Okay, and I have put loads of stuff down in Edmodo for people. Now, hence, Robert, what you've got here, and this is where this all comes in. Oh dear, don't want to do that. Hold the pen, go with the black pen. Is you know already phi is equal to BA. Therefore, n phi we say is BAN, which is going to be BAN. Okay, now here as shown before as a sinusoidal waveform where you go to plus BAN minus BAN, but you can see here this is a cosine function. Now what we can do then is you could write this down as your n phi is simply going to be n phi, and then you're going to have cos 2 pi ft, or you can write down n phi cos omega t. You've seen this with simple harmonic motion where we had displacement x was going to be a, which is the amplitude, sine omega t, or a cos omega t. There's exactly the same equations coming in here. And it shows it changing with time. Now, the thing to remember is the EMF induced is going to be minus delta phi over delta t. Hence, here the gradient is 0, therefore the EMF induced can be 0. Here is maximum negative, therefore it's going to be over here. The gradient is 0 just here. Here is going to be maximum positive, therefore ends up being maximum negative. Hence, you get this waveform popping out just like that, which is shown in the simulation before. Now, to go with that then is because EMF is the rate of change of flux. This is where the sign comes from, because the sign comes from cosine. So all you're doing is you're differentiating n phi sine 2 pi f t. Okay, but we know this is going to be differentiating. Sorry, apologies, Robert. That was going to be cosine there, wasn't it? I had my previous slide. You saw that mistake, didn't you, Robert? Yeah, of course did. Therefore, you got cos 2 pi ft. Now, the cosine goes to sine. But here, you've got a function of a function. Therefore, the 2 pi f pops out. Hence, the EMF pops out to be BAN, which is that n phi you've got here. Then you've got your 2 pi f. And then you've got your sine 2 pi ft. It all looks very messy, therefore we say the angular frequency is 2 pi f. So it pops out the EMF then is going to be BAN omega sine omega t. Sometimes it's written out as down as omega BAN, and then you've got your sine omega t. But this is the bit I'm interested in. Now, that one, which really makes sense, that is what the peak EMF is. Therefore, we say the peak EMF, the E naught, equals omega BAN, because that's the maximum value this can be. Sine omega t goes from a range of 0 up to 1. Therefore, it does make sense that the biggest value the EMF can be is omega BAN. Hence, the peak EMF is omega BAN. Therefore, the equation pops down is to that equals E naught sine omega t. And that's where that comes from. I think that's what you'll be asking about. Now, to answer then, there's the EMF being induced going down like this, and that follows the equation E equals E naught sine omega t, like I showed in the previous slide. Now, all this comes in here is this came from the equation before. We saw in a wire it's moving, the EMF was going to be BLV, where V is going to be the velocity. And what happens then, if you've got N, is going to be the number of turns. Therefore, it's going to be NBLV. And because you've got, yeah, that won't pear-shaped, no. Try that again. That is then going to be NBLV. And because you've got two sides of the coil, it ends up being 2. Now, you haven't asked me about the 3-phase. I'll leave that alone. But then you asked me about then is, oh dear, is, I think it was coming up here, one of the questions I put through, which comes in here. Now, in this one, you've got an AC generator of 80 turns. You've got a length of 65 millimeters and 38 millimeters, and you've got a frequency of 50 hertz and a flux density at 130 milliteslas. Okay, now I go through backwards in this one here to show first of all that the peak voltage is 8.1 volts. E naught, okay, equals omega BAN, and I'll leave you to do this yourself. The area is simply going to be your 65 times 10 to the minus 3 multiplied by your 38 times 10 to the minus 3. Okay, your B is going to be your 130 times 10 to the minus 3 here, and then your number of turns N is there, your 80. It's going to be your 80 turns. Now, to work out omega, you simply use omega equals 2 pi f, and you've got the frequency ready. It's going to be 50 hertz. Okay, which is 100 pi, isn't it? That gives you a maximum flux linkage, and then what you can do is use the maximum EMF, okay, coming back from this equation here, is 2n BLV. So your maximum EMF is then going to be 2n BLV. You'll find you get the peak voltage 8.1, so that's going to be 8.1. You know n, you know your length, you know your velocity, you know your B and your L, therefore you can find the velocity and you'll find it comes out at 6 meters per second. Okay, now I hope that's answered your questions, Roberto. Mr. Mumford signing out.